Okay, as you can see here, we are going to be looking into the next unit, circular motion and energy in space. Our main ideas we're going to be looking at: recognizing circular motion visually and by description, understand the application of force dynamics when the nature of acceleration is the altering of the direction of velocity only, and the magnitude is going to remain constant. Now, what does that mean? That means if I was moving in a circle, say driving in my car around a circle, I would not be speeding up while I did that. I would just keep my speedometer reading the same value, and I would just move around in that circle. Those are the types of problems we are looking at, so that the net forces are remaining balanced the whole time. Then we're going to analyze problems involving variant forces, which should ring a bell as a energy style of problem, and that'll be the back end of this unit. So you may want to copy those notes down right there. So just pause the video right now and get those into your book. Okay, going from here, we are looking to have the skills of recognizing circular motion. Circular motion, if you saw it in real life, you realize something's going in a circle. The type of circular motion that we study, the speed of the object is consistent as it transverses the circle. So the only thing altering about the acceleration is the direction. So our skills are going to be focused around recognizing circular motion and the direction of acceleration, acting toward the center, for a net force which causes a circular pattern to be transversed, and examining the forces acting on an object like we did in dynamics. So we'll find ourselves having two dynamics equations. One equation where we are summing the forces that are acting at a right angle to the plane which passes through the center of the circle being transversed, and a sum of the forces acting in the plane that passes through the center and contains the circular path. You should pause the video here and get what you see there on the page down. Now we're going to examine different situations where there is circular motion. Somebody riding on a Ferris wheel, which is what you see a picture of here. We're only going to examine people on the Ferris wheel right at the bottom or right at the top. In this case, looking right at the top, you're sitting in one of these, you will feel the seat pushing up. There will be a normal force there. There will also be gravity. If you're dead center at the top, that will act right through the center, and the normal force will be pointing exactly away from the center. That peculiar case is where we will examine it, because it makes everything easy for us in Physics 12. So we will find ourselves recognizing these two forces and that acceleration is toward the center. So moving that out of this so it's a little easier to see, I have a normal force. That's the chair pushing up on you, preventing you from falling to your dissatisfaction, no doubt. Fg acting downwards, and the direction of acceleration is towards the center. These are all in line. Now from here we get an equation. That equation, in this case, will have Fg positive because it's moving in a circle. Fg is winning in the sum of toward the center of this circle being transversed, and it equals mac like that. Mass times acceleration. This acceleration is centripetal acceleration, and we will see that it has a different form. Okay, we're now going to examine this one here. We have a toy van on top of a record player. Imagine this record player is going around and around. But let's draw that right from the side, where here's the center, there's the record, here's the vehicle sitting on top. Okay, so here we have the van. We're facing it directly, center of the wrecker there. Then we have the forces acting on the van, normal forces that we've seen in any dynamics problem. Fg is downwards. In this case, we have a force acting towards the center. That force is friction. And from here we can see we have direction of acceleration towards the center. There's no acceleration up and down. We end up getting two equations for this problem. An equation for each dimension. Fn minus Fg, that is the sum of the forces in the y, is going to equal mass times acceleration in the y. There's no acceleration up and down, so that equals 0. That's one equation. And then the sum of the forces centripetal equals MAC. We have only one force. It's the force of friction. That equals MAC. So you can see it's really just like doing a dynamics problem in the setup. It's just our direction of acceleration is towards the center of the circle. I'm going to jump down an example here, and we'll come back to these other ones that are a little bit more difficult to perceive. And we have here, this is a picture of the sun. So here's the sun over in the corner, and we've got the planets all lined up. If I was just put one of those planets out here like this, then we witness one force acting on that. That one force is the force of gravity. Notice this object is already moving, and we know that if it was not moving in the first place, there must have been something pushing it. That push must have been on a tangent to the orbit that the Earth, in this case, moves around the sun to get it going in the first place. And this is why we talk about how this was a gathering of material in that spot, and its rotation rate matched well with the forces and so on. So its tendency, its inertia to get away, is balanced by the force of gravity. And we end up having that orbit there was not caused by some external force. It was caused as things began to spiral and gather in mass. So this is what some of the theory of how our solar system has developed in other solar systems. But back to just how we're looking at it, we got one force acting on that. It's Fg. It's toward the center, the sun being at the center of this circle. And there's only one equation. That equation is Fg equals MAC. We are summing the forces that participate in that centripetal motion equals MAC. There's only one force, very similar to the type of stuff we saw in dynamics. The bottom here we see an example of an airplane going in a loop. At any one time we can look at the forces acting on that airplane, and we will find it's easiest to examine it normally right at the top. The side is a little bit peculiar. We could do it, but we won't be doing that as a problem to solve. Now back to the angle type problems. So we've looked at two that are the two dimensions are not, there's no interplay, there's no forces that are acting in more than one dimension. If we look at this example here where the girl is holding onto a plane that's moving in a circle around her, if I looked at that right from the side, I would see the plane is being held by a string which is not straight sideways, but in fact acting on an angle. So that's the force of tension, and there'll be a force of gravity. And the circle is this way. That would be the center of the circle over here. So what we realize here, like a dynamics problem where the forces are acting on an angle to the accelerating plane, we will have to resolve any forces on an angle to the accelerating plane. This is the angle, and that force of tension will have two forces. There'll be what we might call Ft C or Ftx, and a y component which could be drawn there or over here, Fty. So if we drew this over here instead at the point where it's acting, then we could see easily that we have two forces acting in a plane perpendicular to the plane of acceleration, which is where the circle lies, and one force acting in the plane of acceleration. So our two equations are sum of the forces in the y equals ma in the y, no acceleration up and down, so we get Fty minus Fg equals 0 as one equation, and our second equation, sum of the forces centripetal equals mac, and there's one force, Ftc we called it, equals mac. So now we've set up four problems here where we've just established what the dynamics equations are, and from here we can start substituting values that are given in a problem. So the challenge here is to first set up the problem in the perception of the physics that's being provided, centripetal motion. This is how we look at it with centripetal motion with dynamics. And once we have those equations together describing each dimension, then we start solving for unknown variables. A real world situation, if we were to solve for some unknown, we'd have to know the other values, have to be able to measure them in some fashion. The top one here, I don't know if you can see this very well, but I will talk about it, and maybe you can use your imagination a little bit and get this one figured out. Okay, if you look at this and focus really hard, you can see somebody standing on a chair. So this is a gravitron, so you have a bowed room like this, and people will sit in chairs along the side. So I'll draw, if there was somebody on this side and they were just standing there, they would be like this, pressed against the wall, and then this thing rotates about an axis. The axis is always important. We could have drawn that in each one of our problems as the center, and we resolve our forces into, and maybe this will be a little bit easier to see in this case, we'll resolve our forces toward the center and at a right angle to the center. And now you can see that center of rotation. In this picture, this guy's standing back here. I'm going to draw him from the side to make it a little bit easier. He's standing like this on the chair. So as he's spinning around like that, he's able to balance because of the forces there. And the forces acting on this person are a little bit more involved than we've seen. This is the most involved one I think we're going to have a look at. We have a normal force straight away from the chair. We've got a force of friction, which could be either way if it's spinning fast enough, but I'll presume that it's holding him upward, so it's parallel to the surface he's standing on. There is gravity. And those are all the forces. Now we can see further that the direction of acceleration is towards the center like that, and any force that is on an angle other than 90 degrees to that plane of acceleration needs to be resolved. So Fn will have to be resolved. And the force of friction is on an angle. I'm going to draw a free body diagram right over here so it's a little bit easier to witness what's going on. Force of friction. Normal force. Fg. Direction of acceleration is like this. So it's a little bit easier to see now that we will have to resolve this and this one. So I'm not going to label those on the drawing just because it's a little bit busy already. I'm going to write to the side here what the equations are going to look like. So we have the up and down forces going together to produce no acceleration up and down in the plane that is perpendicular to the plane of acceleration. So we have the force of friction, which I'll call force of friction Y. I'm going to call that theta. And I'm going to call this one alpha. Force of friction Y plus Fny minus Fg equals 0 because there's no acceleration there. And I can make some substitutions just like we did when we were dealing with dynamics before. This is the force of friction, and it is a sine theta plus Fn sine alpha. And to save a little bit of room, I'm going to move that Fg to the other side. Okay, so there's one equation. The other equation has to do with the centripetal components. I'm going to put this up top just because we're a little bit crowded here. You can see we have Fn in the x and minus force of friction in the x. That's a minus equals MAC. In the same way we made substitutions of sine theta here, we'll make substitutions of cosine theta there. What the sine theta and the cosine theta do in these substitutions is give you the percentage of the full force of friction that is acting in that plane. This sine theta gives you the percentage of the force of friction which acts parallel to the plane of acceleration. Oh, sorry, this one is perpendicular to the plane of acceleration. So what fraction or what percentage is this of the full vector? And over here, if I'm using a cosine, I'm going to get the percentage of Fn, which is acting in the accelerating plane. So that gets us to the point where we can start solving some problems using values given to us in problems. That is the nature of solving every centripetal motion problem that we're going to have a look at. And the next bit we're going to have a look into is the conservation of energy principles. As they pertain to circular motion, that is. So this is what we've just looked at. We have looked at this idea of solving circular motion problems. And you can see the steps there. We have identify the direction of acceleration, which is towards the center. Label all your external forces, resolve any forces on an angle other than 90 degrees to the circular plane into components. And we get those two equations which we saw on the paper that we were doing. Here I'm using a notation of some of the forces which contribute in centripetal fashion equals MAC. Some of the forces without any effect on the acceleration, those are perpendicular to that plane, and they will sum to 0 since there's no net force perpendicular to the plane of acceleration. And we have this other point here which I will leave up for a bit so you can copy this down, you give it a pause I should say, and you can see that AC for centripetal motion equals v squared over r, and velocity is talking about a circle, and so we could make a substitution into that of 2 pi r, where r is the radius of that circle being transversed and t is the time taken to transverse that circle. So we can make a substitution of that v equals 2 pi r over t into the equation of AC equaling v squared over r, and we get a new expression for AC. That new expression is 4 pi squared r over t squared, and that'll be on your formula sheet. As long as you know what t stands for, it's not just any time, it's the time it takes to go around a complete circle. That does it for the circular motion stuff. All we're going to do now is ask you questions about different variables that you've witnessed in our conversation here. And you have to recognize what variable am I being questioned about and how do I describe that variable. If it's a vector, I'll need some direction and magnitude. and that's really where we go from here. And so you can be watching for some questions showing up on the website. Okay, I thought I should make a bit of a mention. I've readjusted the page here so you can have a look at these notes that I put up earlier. Notice the one thing that you should be able to see here that you didn't see moments before is that the velocity at the bottom equals 2 pi r over t. Spoke of it, I just recognized I couldn't see it in the video. So there you have it. Make sure that's in your notes.